I'm here representing Hiiroc. I'm here to talk about our new transformational new process for affordable clean hydrogen, and we'll talk a little bit about how that might be relevant to the healthcare estate going forward. So imagine if you had a box, and that box takes in a little bit of electricity and a hydrocarbon fuel, which might be fossil derived, but it also might be biogenic. It might come from biomethane. With a bit of clever technology, you're able to effectively split that hydrocarbon into its core components. So effectively, you've got the hydrogen, you've got the carbon, you're leaving the good bit, the hydrogen, which you can use in a fuel cell, you can combust and you end up with energy and water. And the carbon doesn't end up in the atmosphere, it ends up in a solid carbon black form, which you can use in industrial products. It's got a huge amount of value and a huge market today. Potentially new markets such as use in cement, in soil sequestration, in soil enhancement, and none of that carbon ends up in the atmosphere. So effectively you're decarbonising that hydrocarbon, you're still releasing the energy inherent in it. Hydrocarbons are fantastic fuels, but you've got none of the emissions. Imagine what you could do with that box. So you've got a hydrocarbon waste stream that might get flared off, for example. You could take the carbon out of that. You've got you've got a heater building, you've got a heater hospital, you've got a CHP, you've got all the infrastructure, the existing infrastructure, the gas, the electricity. You can take the carbon out of that. If you've got biogenic feedstock, as I said, you've got the ability to remove atmospheric CO2 from the atmosphere through biomass, sequester the carbon in solid form, and you've got an end-to-end carbon removal. So the kind of uses of that box, frankly, are mind-blowingly versatile. And of course, one of those uses is for industrial heat decarbonisation and hospitals as well. So it's not going to surprise you to know that we as Hiiroc, we have that box. We have a process that we call thermal plasma electrolysis. So it's electrolysis of hydrocarbons. It's not electrolysis of water, where you're ripping apart something that doesn't really want to be ripped apart, and you end up with hydrogen, and you end up kind of back at water. You're releasing inherent energy that's already in hydrocarbons. So the way that process works is we have very sophisticated. The chemistry is pretty easy. The physics is a little bit more tricky. We've got plasma torches that create a very strong electric field. They create a thermal plasma. Because that plasma, the electric field is kind of rips apart the hydrocarbon to kind of form this plasma. Because it is very hot, the reaction happens very quickly. You get very complete conversion of the hydrocarbon. You get a very pure form of hydrogen, a pure form of carbon black. That plasma then immediately gets quenched. The carbon is kind of quenched out into solid form. We separate the two. We collect the carbon. We flow the hydrogen. You've got the carbon out of the hydrocarbon. So a few kind of factors that I'd draw attention to. Lots of processes are chemically very similar. We haven't found anyone who is able to complete the conversion of the hydrocarbon to such a degree in a continuous process in a small modular way. So that's kind of hence the world-leading piece on the top left. Because you're effectively using the same feedstock and roughly the same power, it's the same energy intensity as SMR, so using natural gas, but without the emissions, without the need to capture CO2 and deal with gaseous CO2. You've got a solid carbon black, which is a much more easy proposition to handle. The efficiency, if you've got an existing gas supply, if you've got an existing electricity supply, you can make hydrogen where you actually want to use it, as opposed to where the energy happens to be. Now, hydrogen is a very difficult storage medium to move. People are talking about compressing it or putting it into an organic hydrogen carrier or ammonia or liquefying it. Each of those elements has a cost, has complexity. But actually, if you're using the existing infrastructure to make the carbon where it's needed, you don't need any of that. And actually, you're leveraging what's already there, what the infrastructure we've built the economy on for the last 150 years or so. You're able to leverage. I touched on the versatility. If you had that box, we'll talk a little bit about what else you can do with it. Scalable. So we have centered around a 50 kilowatt torch as being the optimum for the kind of the scalability and the modularity that we're looking for, which means that we can address pretty much any scale. We want to get really, really good at making those standardized units, churn them out, go down the experience curve, leverage the economies of scale, and if you end up with a box like that, you can then tackle any scale. So from small modular units to racked and stacked to big industrial utility scale units as well. So that distributed hydrogen production from small to large scale. And it's also worth mentioning the carbon black. I mentioned carbon black is actually it's a common industrial material today. Most of you will come, well, many of you will come in on the by car or by coach or by bus. You know, all the tyres actually contain 80% of the world's carbon black. 18 million tons of production. Most of it goes in tyres, in coatings and inks, in a number of different kind of use cases. That market exists, and the way that carbon black is made today is horrible. It's made by kind of partially combusting oil. It's very emissive. You get lots of other nasties that you have to take out. So actually, as a co-product, being able to displace some of that very dirty and emissive carbon black production with kind of hydrogen production that's happening anyway is another huge advantage. I mentioned some of the sectors that this could be used for. Abating emissions, like it or loathe it, you know, the economy for the last 150 years has been built on fossil fuels. If there's a way to immediately or very rapidly decarbonize that, that's what we need to get to. You know, Paris requires us to halve our emissions as a globe by the end of the decade. Green hydrogen, renewable energy, you know, the other levers or the tools in the toolkit are not going to come in at scale until the 2030s at the very earliest. So what can we do now? What lever can we pull today to decarbonize our current system? That's all about abating emissions. As we get to that hydrogen economy, we start seeing, you know, potentially kind of big trucks, buses, potentially even aeroplanes powered by hydrogen in a very clean way. And that hydrogen needs to come from somewhere. TPE and this kind of process needs to be or should be part of that mix. It can't all be water electrolysis. It's a very energy intensive way of making hydrogen. We have a lot of fuel, we have a lot of biogenic feedstocks we should be making the most of. And then finally I mentioned, if you're using biogenic feedstock, it is a CO2 removal. There's a vast demand. Again, the IPCC estimates that we need to be removing 10 gigatons a year of CO2 by the end of by 2050 in order to have a chance of meeting Paris goals. So actually, again, this is part of the mix. If you're permanently sequestering the solid carbon black from your biogenic feedstock, that's atmospheric carbon that's going nowhere. That's coming from the atmosphere and staying where it is. So why is this? I'm going to skip forward just a little bit. Why is this relevant? I will just kind of touch on carbon black. So we know that hospitals, for example, and healthcare estates, you don't necessarily want or need carbon black. It's a co-product. It's something that we would manage for you because there is a huge demand. And part of the services that we would provide as Hiiroc is taking that carbon back away, finding a home for it, potentially offsetting some of the cost and sharing those revenues. We're really excited about the prospect actually of carbon black. It's a very simple, kind of quite unprepossessing little powder, but the things you can do with it are quite exciting. You know, I mentioned soil enhancement, which is kind of down at the bottom, agri-feeds. It adsorbs a lot of kind of phosphorus and nutrients, so it can be used to kind of slow release fertilizers kind of more slowly into the soil and avoid that kind of fertilizer runoff that causes so many agricultural problems. There was a paper released over the summer by MIT. They've worked out that if you mix concrete and carbon black, you end up with veins of carbon black through the concrete. It doesn't affect its strength in any way, but it enables it to act like a massive capacitor. And they think that actually a typical house with 45 cubic meters of concrete in the foundations can hold a day's worth of energy. Just imagine kind of the power of that combined with, say, wind turbines or solar panels. So we're really excited about the prospect for carbon black as well as hydrogen. So why are we here at IHEEM? Why are we talking to Seth and hopefully talking to many of you? Well, we have a partnership with Centrica. Centrica are one of our investors, our early Series A investors. We have a couple of things we're doing with them. One is around decarbonising gas peaker power stations, which I won't go into a huge amount of detail there, but it's very exciting as a way of managing the intermittency of the grid and intermittency of renewable power, wind and solar, etc. We'll need gas peaker power stations if we keep decarbonise them as a society. That's got to be a good thing. But the other thing you can do, if you already have a CHP, for example, you've already got the gas infrastructure, the upstream infrastructure, you've got the downstream infrastructure, you've got the power, the heat networks within your hospital. If you're looking for a way of decarbonising that, taking the carbon out at the point of use might be a great fit. And that's kind of one of the products that we are one of the partnerships we have with Centrica Business Solutions, to see whether that might be feasible. It might be a really good fit for industrial heat. So, for example, a deployment at a typical hospital, if we had just one HICOM unit, which is 4 torches, it produces around 400 kilos of hydrogen a day. So that's 126 tons of low emissions hydrogen a year. That would avoid over 1,500 tons of CO2 entering the atmosphere directly from that Scope 1 emissions from the hospital site. And also another 400 tons of a very valuable carbon black, which in addition to the Scope 1 reductions would also displace 800 tons or more of Scope 3 CO2 emissions from that carbon black reduction. So the people buying that carbon black are also going to save their life cycle emissions. They'll thank you. There may be a carbon credit available in addition. As I mentioned, it utilises that existing gas and electricity grid. There's no huge infrastructure work required. It's about as plug and play as you can get. And just in terms of, it's much, frankly, you're releasing the energy inherent in the hydrocarbon rather than ripping apart water, so it needs much, much less energy. So if you have solar on the roof, or you have a private wire connection to a solar park down the road, you can get much more heat from the same amount of power. And it's small. It fits in the footprint of a standard shipping container, so it's around about a parking space. Now, of course, there are many health estates which are space constrained, but it's a couple of parking spaces. If they have a car park, it doesn't take up a huge amount of room. So, some considerations. Clearly, we'd want to talk to you and understand the feasibility, do a little bit of work to understand the specific challenges and considerations for every trust. Clearly, it's about the reason you're doing this would be for decarbonisation. That's the idea. The techno-economics would have to stack up. We need to make sure that the numbers would work. There may be some support. There's government schemes available. We have direct experience with the hydrogen business model, the IETF, the Industrial Energy Transition Fund, the IFS. So and the hydrogen business model, for example, is there specifically to bridge the gap between the cost of fossil fuels and the cost of hydrogen, recognizing that initially there's going to be a gap. We talked about footprint. Clearly, there's very low tolerance for any kind of disruption for hospitals, and resilience is key. There is carbon black, so we produce a solid. We need to make sure that there was a mechanism and a clear process to take that off site in as kind of seamless and painless way as possible. We've spoken about power and gas requirements. We'll be using the gas, that we'll be using the power that you already have, but we need to make sure there was sufficient headroom. As ever, permitting and planning is always a key consideration, but it gives the advantage of being able to use the existing infrastructure and minimising the capex outside the unit. Just as a bit of a summary about where we are, so we were founded in 2019, and that initial science was proved in the lab with 99% conversion, independently verified by SGS, of methane by the plasma torch back in 2019. And since then there's been a lot of focus on operationalizing that, turning it into a product. We demonstrated that at kind of demonstrator scale in our kind of lab and engineering center in Hull last year. We've got 2 pilots live. You can see there our first 2 pilot units operating at a Centrica site at Brigg, as I mentioned, the gas peaker station. That's a project partially funded by the Net Zero Technology Centre in partnership with Centrica. And we're doing an awful lot of work there in product development as well as testing that use case. And we're well positioned for continuing that product development to roll out multi-torch unit at a commercial scale next year. So for projects next year, 2025, 2026, we're talking to clients about feasibility studies, front-end engineering design, etc. today. We've flown under the radar for a few years as we've been developing our product, but we've been emerging from our shell in the last couple of years. So we were, just a few kind of highlights, we were crowned, as it were, the winner of the KPMG Global Tech Innovator Challenge for the whole of Europe. So we won the regional competition, then we won the national competition, then we won the European competition last year. So from over 1,250 entries. We were nominated the FT Tech Champion last year. There's our CEO talking to the King about biomethane and hydrogen production. We signed an MOU with the Egyptian gas company at COP27 last year around flare gas mitigation. And I mentioned the NZTC project. We're working with a lot of different clients on different applications. So just to summarize where we are, it's world-leading proprietary technology we call thermal plasma electrolysis. It provides affordable, clean, scalable hydrogen, as cheap as SMR, but without the CO2 emissions, much more energy, much more hydrogen per kilowatt of energy than water electrolysis. It takes the carbon out of hydrocarbons while leaving the good bit. Enables flare gas mitigation, so instead of just burning this stuff, we can take the carbon out and CO2 capture. You can see some of our Series A investors on the right-hand side, some big names, lots of corporate investors who are interested in long-term partnerships. And yes, if any of that is of interest, then please do contact us to find out more. Any questions? Stunned silence. I'll take that.
Can I ask a question? So the flare, you have 50 kilowatts, 50 kilowatt flare. No.
It's a 50 kilowatt torch.
50 kilowatt torch.
Yeah, so the torch it takes 50 is a.
So what's the temperature?
So the temperature within the plasma is several thousand degrees. It's very, very hot, just for a couple of centimeters, and then that gets that gas then gets quenched in a reactor kind of downstream of the plasma torch, and it cools down very quickly. So the quicker we can cool it, the greater the conversion that we get.
Right. So all that high temperature happens within the container unit?
Absolutely, in a very small localized area. Yeah. Okay, thank you very much indeed for your attention.